So in section 3.3, we're going to be talking about harmonic motion. So when we talk about harmonic motion, we're talking about situations where we have an object that's like rotating. So imagine that we have like a Ferris wheel or something like that. And what we're going to do is we're going to graph our location or height of the passenger on this Ferris wheel on the y-axis and the time that they're on the Ferris wheel on the x-axis. So imagine that we board the Ferris wheel at ground level. If we do that, that's like the first moment we get on the Ferris wheel, and the height of the Ferris wheel is basically at 0. It's at ground level. Sometime later, maybe we're here, so now the height is a little bit higher at some future time. And then maybe we take another measurement here. It's a little later, and we're a little higher. And maybe we get up to here. This is the highest point at some time later. And then when we're over here, now we're a little bit lower, right? And then maybe we're down here. And then we get back to the beginning. We're back to ground zero. And what's going to happen? It's going to start repeating again, right? So it's going to make this kind of looking graph. What would we call this kind of graph? As a name. This is a sinusoid. Is everybody okay with that? Because on multiple trips around this Ferris wheel, the heights are going to be the same again, right? Those are not going to change. We're going to get that repeated periodic behavior like we'd expect from a sinusoid. Okay. So these Ferris wheel questions are common examples. You could also have other things, but you could look at something that's like a weight on a spring is a common example. But let's look at a Ferris wheel example first. So let's say we have a 100-foot diameter Ferris wheel positioned with the center at 55 feet above the ground, and the wheel spins at a rate of 1 revolution per 2 minutes. Construct a function to model the height of a rider, where height is measured in feet and time is measured in seconds, and where the rider enters the Ferris wheel at its lowest point. So I'll give you guys a minute for the people that are copying things down to copy things down. Since I wrote that without actually having to write, I just copy and pasted it from there you go. Since I am an author for this book that we're using, the printed out pages? Yeah. We wrote it as a department. Yeah, Mr. Chun, Mr. Stan, and I have all contributed portions to this text. Well, part of it is because of the amount of material crammed into some of these chapters is a bit overwhelming. Part of it is the sequencing that we want to use for this course that's maybe a little bit different than the way material is ranged in the green book that we have. part of it is so that we have an online resource as opposed to the physical textbook, which there was a push some years back to get everybody to have digital whatevers when they launched the one-to-one program. So there's lots of reasons. All right. So let's start by just kind of drawing ourselves a picture of the situation here, because that, I think, usually helps us understand what's going on. So let's say here's our Ferris wheel. Sound good to you guys? Reasonable proximity of a Ferris wheel. Here's the ground. So we're told that the center of the Ferris wheel is here. So I know that this distance here is how much? 55. I know that this distance here is 50. How did we know that? Good. It's the radius of the circle, which is half the diameter. Okay. So that means that this little section down here is how much? 5 feet. We'll find out in a moment. But I just wanted to draw a picture to kind of represent what it is that we're going to be doing. So the first thing that I want to do, stop talking, please. The first thing that I want to do is figure out whether I'm going to try to write a sine function here or a cosine function here. So why did you say cosine? Yeah, why is it giving us, we're in this, because I don't read the words maximum, minimum in here. So, great. So the fact that we're told that the rider enters at the lowest position means that we're given a minimum to kind of start at. Everybody okay with that idea? If I track back to the example we showed before, we talked about the rider entering at the lowest point. Our graph is starting at a minimum. Everybody agree with that? So we had said before that when we're given a minimum, we like to use cosine. And since this graph is going to start at a minimum, what else can I say about cosine here? Fantastic. The leading coefficient, the a value, needs to be negative. Normally cosine starts at the point 0, 1, which is a maximum. The graph that we're going to draw is starting at a minimum, so I know that there needs to be one way I can take care of that is to have a reflection. That's the easiest way to take care of it. Is everybody okay with that idea? Okay. So let's start sorting through this. Sound good to you guys? Okay. Where's the midline for this function going to be at? The midline is just going to be through the center of the Ferris wheel. Okay with that? What is the absolute value of A, or the amplitude, going to be? Remember the definition for that? It's the distance between the extrema and the midline. It's just 50. Right? If the amplitude is the distance between the midline and the maximum or minimum for the function, that distance is 50 for us. Do you guys agree with that? Just from a visual standpoint. So what we need to do now is we can say that the A then is going to be negative 50, because we know that we said the A was going to be negative. So the last things we need to do are determine the values for C and for H. Everybody's on board with how I found the A and the K? Right?
So for the A, firstly, so why isn't it like 52? Because it's 55.
Okay. Would you prefer thinking about it as that the A is equal to Y max minus Y min over 2? What's the maximum value or maximum height we can attain on this Ferris wheel? That's 105, right? Okay. And the minimum would be 5. So that's going to be 50 as well. So you can think about it that way if you prefer. Okay. Yeah, no problem. So if you prefer to use those old formulas, you can still use those old formulas to do the A and K. I mean, I thought that perhaps visually that would be helpful as well, but yeah. Ah, yeah, so it's still 105 feet off the ground because you're starting not at 0 with the Ferris wheel. Okay, good. Okay, so we still need to figure out our values for C and for the H. What quantity is related to C that we've used over and over and over again? Period, though, right? The part that's going to give me the period is going to be this. So, because if we go back and we look at our previous picture, we did 1 revolution, and what did we get out of that? 1 period. You guys agree with that? Okay. So I can say then, well, remember that it asks us for time in seconds. So I know that 1 revolution equals 1 period, which is going to be 120 seconds. And I know 1 period is 2 pi absolute value C. Might not be very, well, it is really big. Yeah, that is a fast Ferris wheel. So I know that the value for C is going to be 60 over pi. Is everybody okay with how I got that? The last thing I need to do is determine H. This is going to be not terribly difficult, though. So in our parent function, we have a maximum that occurs at 0, 1. In our transform function, we're going to have a minimum that occurs at time 0, and then whatever that minimum value is. Oh, I suppose that's 5 here. So if I do the C times x plus h equals the transformed x, I see that h is equal to 0. That's the advantage of choosing to use a cosine function as opposed to a sine function. So I have negative 50 times cosine of the reciprocal of C, x minus h plus k. And again, you could simplify this stuff down inside the parentheses if you choose to. So I know that to go from a parent function point to a transform function point, I use the transformation cx plus h, ay plus k. So I did cx for my parent function plus h should equal the x-coordinate for my transform function. So h is just 0 when I solve that. Does that feel okay? So the C value I found by noting that 1 revolution is going to equal 1 period. We know that we're told in the problem 1 revolution is 2 minutes, which is 120 seconds. And I know 1 period is equal to 2 pi absolute value C. So I divided both sides by 2 pi. Okay. Everybody happy with that? So, is it terribly different than the problems we've been doing already? No. Let's do one more. Actually, I lied. We're going to do maybe more than one more. This one is just I forgot about this. It's just a continuation. So using our function from above, we're going to start by finding the height of the rider after they've been on the Ferris wheel for 73 seconds. What am I going to do with that? Plug 73 in for x. Really, we probably should have called this h for height and t for time. Let's do that from here on out just to make it a little less, or a little bit more obvious exactly what we're doing here. So I'm just plugging 73 in for t, and then it's calculator time. Come on. There you go. So if I do that, I get 93.86. Those are feet, correct. Part B says a woman's height is 45 feet off the ground. How long may she have been on the Ferris wheel for? I'm going to plug 45 as a height. So I'm going to plug that in for h. And then we're going to solve for t. Okay. So to do that, what should I do first? Subtract 55. Good. Then what? Divide by negative 50 to get 1/5. And then how am I going to get rid of the cosine there? What cancels out a cosine? Not secant. Cosine inverse. And then we'll just multiply both sides by the reciprocal. And we're done. When I type that into my calculator, I get 26.15 seconds. Now, is that the only answer? No. Let's see why. So let's say that this is h equals 45 here. So we found this answer. where if this is where we boarded. There's another answer here, but there's also another answer there, right? There's actually going to be an infinite answers. If we knew how long the ride was, like the Ferris wheel ride lasted, we could actually list all the answers, but we don't know that information. But 20, because of the context of the question, it asks just how long may she have been? That just means we need to supply one answer, and the easiest answer to get is this one that we just got. So we're going to leave it at that, but I did want to point out to you that there are more than one acceptable answer on this, because that becomes a really important part in future chapters when we start talking about solving trigonometric equations. Keeping that in mind will be really important. Okay with that? We good on this one? So again, nothing too difficult there. Let's do one more where we have to construct a sinus or a sinusoid here to model the situation, because that I think tends to be the most difficult one for most of us, or the most difficult kind of problem for most of us. So at 5:15 a.m., high tide comes in on Siesta Key, Florida, and the depth of the water is 18.3 feet. At 11:27 a.m., the depth of the water at low tide is 11.8 feet. Model the depth of the water using a sinusoidal function, and then we'll find the depth of the water at 8 p.m., and then when the first high tide will occur the following day. So, what kind of function should I be using here? Sine or cosine? Cosine. Why do you say cosine? Yeah, so when I see high tide, what I really think of is maximum. And when I see low tide, I really think minimum. Everybody's okay with that? So I know that K is Y max plus Y min over 2, which is going to be 18.3 plus 11.8. And when I compute that out, I have it here in my notes already, so I don't need my calculator, I get 15.05. Similarly, I can find the A by doing Y max minus Y min over 2. And when I do that, I get 3.25. Is everyone okay there? Okay. To find the period, I need to look at the, well, how much of a period do we have going on here? We go from max to min. That's half a period, right? So that's going to be 11:27 minus 5:15, which is 6 hours and 12 minutes. But we should probably convert this into a decimal, right? Because I can't really add or do computations involving time with it written as like hours and minutes like this. You guys agree with that? We could convert this into hours or into minutes. Either would be acceptable. I'm going to choose to convert this into hours because 12 minutes is how much of an hour? 1/5. So I'm just going to write it as 6.2. 12 divided by 60 is 0.2, right? Okay. So I know that one period then is 12.4, and that's equal to 2 pi absolute value c. So that is going to be 6.2 over pi is going to be C. And the last thing I need to do is figure out my h. So in my parent function, I have a maximum that occurs at 0, 1. In my transformed function, I have that a maximum occurs at 515, comma, whatever that number was, 18.3. So h is going to be just 515, right? But I don't want to write it as 515. I want to write it as a decimal again. And because I chose to write my first time in hours, I'm going to write this time in hours as well. 515 is the same as 5.25 hours. So I can say then we have, and because we're going max to max, obviously, the A coefficient is positive. So I have, let's use H's and T's here and try to be consistent. H is equal to 3.25 times cosine of pi over 6.2 x minus 5.25 and then plus 15.05. So that's our answer for part A. Part B asks us find the depth of the water at 8 p.m. So all I need to do is plug 8 in for T, right? Nope. 8 p.m. is actually 20 hours, right? So I have to plug 20 in for T. I tricked you there. But after you've seen the trick, it's unlikely you'll be fooled again, because you guys are quite clever. And when I type that into my calculator, I get about 16.26 feet. Part C says, when will the first high tide occur the following day? So on day 1, I have high tide at 5:15. Right? We're told that in the problem. I know that the period is 12.4 hours long, and 12.4 is really 12 hours and 24 minutes. .4 times 60 is 24. Everybody's okay with that? So my next high tide would occur at 5:39 p.m., but that's still on day 1, correct? Everybody agree with that? My next high tide would occur adding 12 hours and 24 minutes. What am I going to get then? About 6:03 a.m., and that's on day 2. So that would be the first high tide on the following day. Does that make sense to everyone? I'm just adding some hours and minutes there until I get a time that's in the following day. It's probably the easiest way to attack that. What do you guys think? For tomorrow, I'd like, we don't meet tomorrow. For Wednesday, I'd like you to work on 27 to 30. I'd also like to point out, too, that I've posted the review for Chapter 3 to Power School, along with the key for the review, so you can start on that if you'd like. On Wednesday, our plan will be to take final questions from this section and or the review, and then I'd like to do the Chapter 3 test on Thursday and have that out of the way and be able to enjoy your long weekend to party down, dude. Or, like, do some homework and get caught up on things and do some community service.